Start.
Yeah.
So hi everyone. It's a pleasure to introduce Eric Andersson, who's our seminar speaker today. Eric did his PhD at Lund University in Sweden with Oscar Eggers and Florent Renaud. Eric is an expert on galaxy formation. He's worked on a lot of topics from globular clusters, runaway stars, star formation, and feedback. Most recently, he's been working on some very impressive star-by-star simulations of entire galaxies, and he'll tell you more about them today. So,
thank you very much. Hi everyone. I've been warned that you might interrupt me during my talk. That's absolutely fine. I prefer it that way. I'm from the American Museum of Natural History, where I'm currently working as a research scientist / postdoc. And I'm going to talk about what I'm showing you in the background here. This is a simulation of the formation of a dwarf galaxy, one of the smallest galaxies that we find in the universe. And as I will show you, or as I will build up throughout this talk, is that in these types of simulations that we have here, we can now resolve individual stars. And I'll get into why and how we do that. So I want to start with a bit of an anecdote. I'm coming from the Museum of Natural History, so I thought it'd be appropriate to start talking a little bit about culture, and especially historical anecdotes. So what I'm showing you here is a symbol from Norse mythology. I myself grew up in Sweden, so it lies close to heart. It's a depiction of an Ouroboros snake, or a snake that is eating its own tail. This particular example is the Midgard serpent, which is enclosing the world tree, or Yggdrasil, in Norse mythology. And this is a symbol that is very common in different cultures, especially in historical context. And it's been used to symbolize cycles, especially in nature. And galaxy formation is no different. We typically talk about this in terms of a baryon cycle or a feedback cycle, where we have gas accretion, we have star formation. This leads to energy injection into the interstellar medium, which leads to the expulsion of gas from galaxies. And this kind of closes the loop when this material is then mixed and then accreted onto the galaxy again. And this is quite nicely depicted by this image here by Andersson et al. 2017, where they describe this cycle in the annual review. We've realized that getting this cycle right is crucial for getting things like mass, size, chemistry, and internal structure of galaxies correct. But the problem is that there's actually a lot of complexity and a lot of scale coupling. So better depiction of this cycle may be something like this, where we're actually going back and forth, and we have to think about a lot of the details. For example, the initial mass function for stars, stellar evolution, clustering stars, etc. And these are the details that I will talk about here today. Because this is a complicated problem with scale coupling, a lot of the effort on this topic has been involving simulations. And these have been very successful. Modern simulation nowadays, I would say, they manage to capture a lot of the global properties. And this is particularly because of this feedback cycle. We need feedback to solve a problem that we typically refer to as overcooling, where we just accrete too much mass. And I would say the very, very broad range of simulations that we have now, we're able to recreate these things. They're also able to recreate emergent phenomena like scaling relations, for example, the mass metallicity relation. But there is, of course, still a lot of open questions. I'll touch on a few today. Some of the ones that I've been mostly interested in is star formation and feedback in a multistellar, multi-phase interstellar medium. We also have highly detailed spectroscopic surveys, so we have a lot of interesting data that we can use to constrain different models. And it turns out that things like chemical yields and chemical mixing are not very well understood. There's also a link between observation and models that I will make by the end of my talk. So one of the efforts that we've seen in the more recent years is towards what people like to refer to as result simulations. I have quotes here. to keep that in mind. There are still, of course, things that we cannot resolve in these simulations. But within the galaxy formation community, this type of simulation are simulations that tries to get the structure of the interstellar medium correct. And this turns out to be crucial for things like stellar feedback and how that interacts with its environment and later coupled to larger scales. Historically, how this has progressed is firstly starting to use stratified disk simulations, where you take something like the Milky Way and then you cut up kind of a chimney from the Milky Way disk, and then you simulate this region at very high resolution or with very advanced models for your physics. But this comes with innate problems from geometry. It's very hard to take into account things like galactic shear and also the dynamics of the disk where this system is evolving. Because of this, we've also seen a push towards simulating smaller galaxies, in particular dwarf galaxies. And in these simulations, we're now reaching parsec or tens of parsecs of resolution in our simulations. These are getting into a regime where we have to start thinking about star formation quite seriously. And one of the later things that have kind of exploded in the literature is what's called star-by-star models. And this is what I will be talking about today. And these are models where we have basically particles that trace individual stars. So we now have to care about things like main sequence stars, AGB stars, also black holes and white dwarfs in these models. Yes?
So what's the state of the art for how large a galaxy can simulate star by star?
Depends on how long you want to simulate it for. I myself have simulated the Milky Way mass galaxy, but this was only for a couple 100 million years, and also with some simplifying assumptions. The simulations where I simulate dwarf galaxies, these are, I will show later, but these are like 10 to the 9 halo mass objects, and these I can simulate for a Hubble time with this model. And to kind of explain how we do this, and a little bit of the details and what shortcuts we can take when we do this, I want to explain first what a non-star-by-star model is, and then I will transition into showing you what I mean when I say a star-by-star model. But the problem that we're dealing with is we want to simulate a population of stars forming groups or clusters. So traditionally, the way that we thought of this is we can just take all these stars that form together and put them into a single particle. And this is typically called the traditional star particle, macroscopic star particle. In a star-by-star model, we kind of cut up the IMF. So I'm showing you the IMF here. And we decide on some mass threshold. And above this mass threshold, we treat stars as individual particles. But below, we agglomerate the mass into a single particle. And the reason why this works so well is because IMF is very steep. So you don't have to introduce too many new particles. And the other reason why this is quite nice idea is the massive stars are responsible for the vast majority of energy injection. So these are actually the stars that you might want to simulate in more detail. Another reason why you would want to do this in the first place comes down to, again, the details of how we model these systems. So here I'm showing you an example of a mono-age stellar population. This is showing the mass injected as a function of time. Here I'm showing you the spectra of this population. This is a population of 300 solar masses, which would be considered state-of-the-art resolution for these types of simulations. The filled lines that I'm showing for different examples of mass injection, for example, AGB in green, winds from massive stars in blue, and then supernova, particularly core collapse in red, is shown here, the median for 300 solar masses population. And the colored region around that is the 68th percentiles. And when you reach something like 300 solar masses, then first of all, just through statistics, you on average have your first core collapse, or the median explosion time for a core collapse supernova in this system is roughly 20 million years. So not the 3 million years that typically is thought of as an IMF average. And it's also within 1 sigma to not have any torque-collapse supernova at all for this particle. The same is true for the radiation output of this population. The red line shows the median, and the black line shows what you would get if you take in fully sampled IMF and then just rescale the mass. And these are not the same. And these are the sort of things that we're after when we're trying to simulate to this level of detail. I have my own model, my own star-by-star model. I call this model Inferno, and this is what I would like to refer to as a flexible star-by-star model that I've implemented in the Ramses code. What I mean when I say flexible is that this mass threshold that we set is actually a parameter in my simulations. So it varies a bit between different simulations. For example, the simulation where I simulated a Milky Way mass system that unfortunately I don't have time to show today, I picked 8 solar masses. And some of the simulations that I'm going to show later has 0.5 solar masses. So you can actually change this and tune this to the problem that you want to investigate. And of course, going lower implies more numerical cost. So it's a give and take.
Maybe you're going to say this, but do you mind if I ask how you actually assign masses and particles in the star formation process itself? Like these red objects, are they forming independently as separate sites of collapse, or it's all being done together from a single gas cell, but you're apportioning the...
Exactly. So the way the star formation algorithm works is we go through the cells and we check for different criteria. And when we satisfy our star formation criterion, we apply something like a Schmidt relation. So we take basically estimate the star formation rate per free-fall time times some efficiency. And that gives us a mass that we want to convert into stars. And at that point, that's when we sample the IMF. And we have an assumed IMF in this case.
And the reason to have them be separate particles as opposed to separate stars identified within a single particle is that you want them to have dynamics?
Partly, yeah. So that's actually the next point here. So one of the, we still have to make assumptions for these models. One assumption is the IMF. Another problem we're dealing with is that we're still not resolving dynamics in these simulations, at least not in a star cluster. These are still collision-less dynamical forces. So I employ tricks to kind of deal with this. For example, I give NATO kicks to stars at birth so that I can get things like runaway stars in these models. And yeah, a way of getting around this problem with unresolved dynamics. I already went through stellar evolution and feedback, but I guess the point is here that we're doing this on a star-by-star basis now. And I also have a fairly advanced chemical enrichment network that builds off yield tables that are available in the literature. And this means that I actually have the majority of the elements available, at least when I start the simulation. When you do start, you need to pick a selection of elements that you want to investigate. And depending on how many you choose, you're also going to increase or decrease the numerical cost of the simulation. But this also goes on a star-by-star basis. So basically for different processes like supernova, winds, post-main sequence evolution, each star gets yields that are injected with the feedback with the correct timing based on the stellar particle's mass or the star's mass and also its metallicity. So summarizing this a little bit in a bigger context. So galaxy evolution is a problem with an extremely large dynamic range. And the star-by-star models that I just described is a way to kind of sit in between the small and the large scales. So we have to make assumptions from the small scale physics like star formation. We have to assume an IMF. We have to make assumptions about the unresolved dynamics, etc. But we can do this in a galactic environment. This example is an isolated dwarf galaxy that I run a couple of years ago. And one of the things that I've worked on for the past year or couple of years is to actually push this Inferno model into the cosmological context. to actually simulate star by star from a cosmological matter distribution. And I've done this as part of a project called EDGE. EDGE is an acronym for Engineering Dwarfs at Galaxy Formation's Edge. It's actually a recursive acronym, for better or worse. I won't acknowledge that back here for the sake of time. But the goal of EDGE is to kind of start simulating galaxies at the lower end on the galaxy mass function. So simulating the smallest galaxies in the universe. These are the fundamental building blocks of a galaxy, or a hierarchical galaxy formation. So we want to make sure that we can actually capture the physics and accurately simulate these objects. And then the goal is to then go up the mass ladder and like try to simulate more and more massive systems. Dwarf galaxies are also very interesting numerical laboratories because it turns out that they're very sensitive to the approximations that we make for the physics that we implement. So this was shown quite nicely by a student in Lund a couple of years ago, Matteo Pergamet, where he tested different assumptions for the feedback physics. And he found that if we look at something like the mass-metallicity relation, you actually move around quite a lot for these dwarfs. Increasing the feedback strength for supernova can move you up and down. You can move around in interesting ways if you introduce variations to your IMF, or also adding radiation, etc. So that's another motivation for this EDGE project, where we're trying to simulate these systems. We also have a fairly extensive suite of simulations that are simulated with more classical galaxy formation model, so without this star by star. So this is a nice set of simulations that I can compare my models with. And we also have these with different types of physics, for example, supernova and radiation, and also just supernova.
Could you say maybe what is the radiation doing? Is that photoionization feedback?
So it's a radiative transfer model. If you know the technical stuff, it's an M1 scheme to trace the radiation. And we trace this in different bins. For example, the optical and UV in one bin. We also trace Lyman burner, infrared, and there's one more that I think there's one of the ionization levels for hydrogen.
Just wondering why it has such a significant impact on this.
There's a lot of things that makes this. Some of them are actually because of the assumptions that were made for the supernova feedback. It's all detailed in this paper. They should be on arXiv. It was recently accepted for publication. But basically what you do when you introduce radiation is you tend to puff up galaxies. You tend to slow down star formation and make it less bursty. So you get galaxies that sit and quite nicely evolve with a constant star formation rate, rather than something that just explodes and then comes together and then explodes, comes together. And at the end of the day, what happens is you tend to reduce your mass loading factors. So you tend to retain more metals. That's why you go up in iron. But you also shift around a little bit in mass. But I think how the metals evolve is more significant, this result.
So, how does the fuse mass vary with galaxy mass at well, I guess at low metallicity environments? I mean, there's a story, for example, you make big black holes of 10 to 4 degree gas. That's extremely ionized. But I mean, is there any systematic difference in G's mass of the gas compared to, say, a Milky Way like galaxy?
That's a good question.
The reason for the question, of course, is that this might connect with the mass function.
Yeah, I'd have to come back to you on that one. I typically think of Dean's mass as something scale dependent, but I haven't thought of it in terms of galaxy scale.
What about cosmic rays?
We don't include cosmic rays in these models yet, but that's something that we want to include as well. I mean, technically they are included in the heating and cooling that we have in the model, but that is happening from fitting functions. So we don't explicitly trace that in this case. Another thing that we pay attention to with these models is the fact that when you're running cosmological simulations, you're losing a lot of the control that you would have if you run something which is more idealized. So to show you an example of this, I'm showing you here the halo mass as a function of redshift for a galaxy that is 10 to the 9 at redshift 0. And this confidence interval plotted here in this gray region shows kind of the different ways that you can get to that mass. So we wanna make sure that whatever conclusions that we make are not super sensitive to just being lucky from the galaxies we selected when we started the simulation. And to deal with this, we employ something called genetically modified initial conditions. Basically what this means is that we pick a galaxy that has some mass at redshift 0, in this case 10 to the 9 halo mass. We have one reference, which is the simulation. And then we go in and we modify the matter spectrum at 30 times very, very carefully to kind of modify how this galaxy grows. So we can have something that grows more rapidly early or something that grows later, for example. And this we do very, very carefully, meaning that on average, if you look at the galaxy, here I'm showing movies of the dark matter distribution, these are the same environment. We're just delaying and changing the mass of when mergers comes in, etc., to kind of get these effects. So trying to be in a very controlled way, change the growth history of the galaxy and see what kind of scatter that introduces to our simulations. So with all those details, the latest thing that I've already shown you this movie, so you already know, but one of the latest things that we've done in this project is to actually introduce this Inferno model that I described before. So we're now running these simulations with individual stars. And we actually go down to 0.5 solar masses for this mass threshold. So the idea here is to resolve the post-main sequence of all stars over Hubble time. So this gives us incredibly high stellar mass resolution. And I'll show you later that this actually gives galaxies, or at least some extended halo populations of stars, shows up very clearly, which before was just a handful of particles. And there's some interesting things that you can study when you reach this level of detail. So giving you an example of with and without individual stars, I'm showing you these two pictures here. These are actually the same galaxy, and this is with the simulated with all the stars. And here's what the equivalent galaxy would look like at the normal edge resolution. These are zoom-in simulations. And for all the simulations that I'm going to show here today, we reach a resolution of roughly 4 parsec. This is at redshift 0. This actually evolves a bit with the expansion factor. So at higher redshift, when most of the star formation is happening, this is more like 1 parsec resolution. And I managed to simulate 4 of these different growth tracks that I explained before. We have 1 reference, and we have 2 that formed later, and 1 that forms earlier. And the reason why this is kind of interesting for this particular galaxy is that these are actually quenched by reionization. So these are reionization relics, and they actually lie at the boundary to ultra-faint dwarf galaxies. And what that means is that when reionization kicks in, we stop forming stars. So whatever your mass was at this point is a good predictor of what your stellar mass is at redshift 0. So if you have a distribution of halo masses here that then end up with the same halo mass here, then you're kind of probing the scatter in the halo mass stellar mass relation. So that is also part of the reason why we're being so careful in selecting these different growth histories. I'm also showing you both with star by star and without star by star. Star by star is these filled lines, and this dotted lines is without the star by star. And one of the things that we find is that star formation regulation tend to be slightly weaker when we do star by star. We also see this when we look at something like the mass metallicity relation, these 4 points here are these 4 star-by-star simulations, and this is compared to the same set of simulations, or not the same set, but say similar masses with a somewhat comparable model for the feedback. And the problem here, at least I think, is that this comes back to this point that the IMF is not fully sampled when we reach these very, very high resolutions. This has been pointed out in the literature before, and this is also what I showed in the beginning. Now I should point out that these particular simulations, these will run without radiation. Same goes for these simulations here. I'm actually running them with the radiative transfer model as well. This turns out to be very expensive. We have to wait a little bit for those results to come out. But my goal is to actually confirm whether this is the case. We actually regulate star formation less when we do this star by star. We can also look at some things like scatter due to the IMF sampling. This particular galaxy I've re-simulated over and over again with different model assumptions, and also in this case with the same model assumption but a different random seed for the IMF sampling. And we do see that we actually do move around quite a bit just by changing what stars we end up sampling. So there's a lot of uncertainty that comes in here. Stochasticity is one, but we also have uncertainties from stellar evolution and also feedback yields. So I re-simulated this model with a set of different yields from the literature. These are yields from Imongi and Kefi in 2018. The fiducial simulations were using yields from the New Grid collaboration, which is Ritter et al. 2018. And these models also include stellar rotation as a parameter, so these are things that we now need to care about. And it turns out that you can move around a bit here. I've also included one model where I have a metallicity-dependent rotation distribution, just to get an idea of what are the uncertainties that we get from these things. Another thing that is not so appreciated in the galaxy formation community, at least I haven't heard too many people talk about it, comes from type 1a timing, especially. So basically what we do when we run these models is that we assume some delay time distribution, or delay time distribution with some rates, but you also have to assume the delay time when you want to start to apply this distribution. And typically you assume 40 million years. You say this is when the first white dwarfs show up, so this is when I can have my first type 1a supernova. But you can easily pick a delay time that is 100 million years. That's well within the empirical constraints. And it would also make sense that you would actually take a bit more time to develop a type 1a supernova than just as soon as you become a white dwarf. So I reran the model, changing this delay time. The fiducial was 40 million years. If I go to 100 million years, we move down quite substantially. And also, if we don't include 1As at all, we kind of move out of this group entirely. So it's quite interesting to see that even type 1a supernova, which typically happens on long time scale, affect these galaxies that formed before Redshift 4. And just to highlight the point of stochasticity from IMF sampling, I also reran one of these other models 3 times with different IMF seeds. And we can kind of see some similar trend where you seem to move along the relation rather than scattering up and down, which is quite interesting. Here, summarizing that more broadly as kind of a takeaway. Basically, we have stellar evolution or yields that kind of scatter us around. We can move kind of this way, just from IMF stochasticity, and then you can also move up and down with type 1a timing. There's more uncertainties here, of course. We haven't even started looking into POP3 stars, but it is very high up on our list to actually start exploring and seeing what happens when we do that, etc. But we wanted to have a firm understanding of what the POP2 stars are doing before we went into this.
If you were to simulate a smaller halo, fill in the trend to the left?
We think this is more to do with POP3 stars, actually. Because now we're getting into a regime where you have basically a single supernova can give you this enrichment pattern. And so and this is really in the territory of POP3 stars.
So do you assume some POP3 enrichment in the beginning of your simulations?
But we just apply a metallicity floor for these simulations. That metallicity floor comes from POP3 modeling community, but we want to actually take this a little bit more seriously and actually introduce a POP3 model, and then pursue these lower mass systems. We're also seeing some interesting thing when it comes to enrichment of your environment around the galaxy. I'm showing you here a fairly complicated plot, so let me go through it. These are all density projections shown in blue to green, just to give a sense of where the galaxy is. Red points are stars that have formed, and these contour lines, the filled line shows the projected iron abundance of -4, and the dotted line shows projected iron abundance of -2. And we're kind of seeing how these galaxies enrich their environment in different ways, depending on how they come into existence. If we look at something like the earlier galaxy, this tends to grow in mass very rapidly early on, and you become kind of a single system that is just polluting its environment. And you very quickly get an average metallicity around this galaxy that is quite high, compared to something like the latest, where, because it's growing so slowly at this point, it's just many small galaxies that is polluting, and they don't have enough strength to get this very substantial enrichment of the environment. So that is something that I'm currently working on trying to quantify. Another way of looking at this is looking at the iron as a function of the stellar ages in the simulation. The earlier one grows more like how you expect a single system to evolve, where you have this nice trend, compared to this guy here, where you just have a couple of islands. And this is also reflected in the star formation histories and the MDFs. It's just splitting up this evolutionary trend, where we have small islands in the MDF. This is now showing both iron and also the alpha abundance. Whereas in the case of this earlier simulation, you have more of a broader distribution that still has peaks, but is more connected. And this actually comes from how long your star formation bursts are. This is showing the star formation rate for the later and latest simulations, and here we can see these are very peaked, very bursty. These are extremely short star formation bursts, and they're quite separated in time. This also gives you these very distinct islands in metallicity. Whereas in these two cases, the star formation bursts are more prolonged, and tend to see that as a broadening of the different distributions in your MDF, etc. So these are all things that I'm currently working on trying to quantify. Of course, there's a lot of complications here. I have all these models with different assumptions for the stellar evolution. Here is how rotation affects this. So now we're only looking at the same galaxy, this GM2 later. This is the model that I've shown you before. And here are the MDFs for just different assumptions for the distribution of rotations, and also what that implies for the different field models that we apply. Basically what this boils down to is a matter of feedback timing and how fast you're injecting or enriching your environment. We do see that when we go to models where we have very strong enrichment very early on in terms of the stellar population, we tend to wash out these islands quite a lot more. So these are uncertainties we need to take into account for this type of analysis. This becomes a whole mess when you then split everything up into different elements. I have 6 elements shown here, all as function of iron, or they plotted relative to iron as a function of metallicity, carbon, nitrogen, oxygen, magnesium, aluminum, and silicon. It becomes very complex. We also have all the different models that I want to compare. I don't have time to go into this into detail, but if someone is interested in looking at this, then I'm very happy to discuss this further. And of course, we also have to take into account the scatter just from the IMF sampling. So for the last part of my talk, I want to switch gears a little bit and talk more about how these simulations compare to observations. And to just give myself a small breather, let's just appreciate the number of stars that we have in these simulations and how nice it looks. Like we can see all this structure in the outer galaxy. This is actually a bit of a cheat from myself. I'm blowing up the color bar like crazy here, so we actually see every single particle in this simulation. More fair galaxy to show you would be something like this. This is now showing the V-band surface brightness of this system, as if it would look like if we observed this at 400 kiloparsec. Now all this nice structure disappears. It's actually quite hard to see here on the projector, but that just makes my point a bit clearer. But this is a very real problem that we have to deal with. And another example of this, which is actually from an observed galaxy, this is Reticulum 2. I like to test my students and ask if they can spot the galaxy in this image. I can tell you that almost everyone gets this wrong. What you need to do is remove the background using some method for member detection. And if you do that, then the galaxy pops out. And it actually covers most of this image here. And to do this member detection, we typically have to resort to spectroscopy. And this puts a limit on the point source magnitude for detectability. This was shown explained quite nicely in the review by Simon in 2019, where he plotted the R-band magnitude as a function of distance. And also these lines here are point spread magnitude limitation for different surveys. We have LSSTs now online. In a couple of years we'll get all this nice data. It will help a lot actually. And this actually limits the total V-band magnitude for a galaxy that you can detect at a given distance. And these are very hard to find against the background. So now we have a simulation where we actually have all the stars, and actually the color magnitude diagram makes sense in the simulation. This is something that you just get out from the simulation directly. So I thought, what happens if I just apply a magnitude limit to this simulation, and then I try to characterize what this galaxy looks like based on the stars that are actually observable. So this example is shown at 400 kiloparsec. I apply the magnitude limit of the dark energy survey. And in this case, this particular galaxy, we can see 49 stars. And these are all on the upper branch of the, these are all on the giant branch of the CMB. And the question is, can we actually characterize this dwarf based on all of these 49 stars? Of course we can. Never tell an observer that they can't do something, because they will prove you wrong very, very quickly. There's actually a lot of clever people working on exactly this problem. So there are methods to actually derive properties, even when only a few stars are observable. So I took a method from Nicolas Martin that he published, and I applied this method to my simulations with this magnitude cut. Basically, what I'm showing you here is the galaxy, or the stars are visible in this galaxy as red points, and then I applied some background of stars, and then I do MCMC fitting to kind of derive things like the half-light radius, and also the number of stars that the method believes belong to the galaxy, and then you can use this to get a Big Bang magnitude. And I did this for all 4 simulations. And I kind of placed them at 400 kiloparsec because this gives me a nice range of stars that are observable in the different galaxies, going from 50, in this case, all the way up to 700, and then seeing a little bit how does this affect the result. And here I'm showing you that. This is showing the half-life radius as a function of total Big Bang magnitude. The simulations are shown with these stars. And when I mock observe them, I get these processes that I'm showing here. And one of the things that I find is that we systematically underestimate magnitudes when we mock observe these simulations. And the reason for this actually has to do with this extended light profile that these galaxies actually have. So here in the black line, I'm showing you the number density for the galaxy as a function of distance. And all these galaxies, they have these extended light profiles, even this example here, although it's a bit hard to see. And these light profiles, they get eaten up by this background term. So you cannot account for this. And that means that you underestimate the number of stars that you believe are members of your galaxy, and you then underestimate the magnitude. And this is not something we actually typically care about in the simulation community. Like half-life radius and Big Bang magnitudes are pretty well defined in our simulations because we know where all the stars are. We know if they belong to the galaxy. But we need to be a bit careful here, because then we use observations to kind of constrain the model assumptions that we have. And this particular thing, like this mock observations, it actually introduces a systematic shift in the mass-metal history relation for these systems. So this is something that I want to emphasize, that when we're doing this kind of analysis from simulations point of view to kind of constrain the models, we should actually take the harder route and do this properly and make sure that we are comparing the same parameters as we get from the observations. Otherwise, it's very hard to take into account these sort of systematic effects. There's another thing here, which is typically referred to as CMD shot noise. This comes back to this IMF sampling and why that is important. These 49 stars are all selected to be on the upper branch, but this kind of depends on exactly what mass was sampled when these stars formed. So just as a test, I did an experiment where I binned the IMF that I had in fairly small bins, 0.25 solar masses, and then I resampled the IMF in these small bins, just to give a small perturbation to each stellar mass. That gives me a different sample of stars that I then use to characterize my dwarf. And if I do this over and over again, I can estimate kind of the error that we introduced by this. And it can be quite significant, especially when you only see like order 50 stars. You're actually moving around quite a lot here. These two lines shows the 68th and 95th percentiles that I get from this experiment. All right, that brings me to my final slide. I've talked about simulations with individual stars, and in particular, I focus on the formation of the smallest galaxies. I hope I convinced you that star-by-star models are important for the next generation simulations. IMF sampling actually is important when we reach these very, very high resolution simulations. There's some interesting questions that are raised. For example, is star-by-star feedback actually weaker? Something I'm working on trying to confirm. I talked about early chemical evolution, and I emphasized that assembly actually matters here, even for very, very low mass systems. But of course, we have to deal with a lot of uncertainty still within our models. And then for the last part of my talk, I talked about these direct comparisons with observed stars. So I will leave it there, and I'm very happy for your attention. Thank you.
Low mass galaxies, don't expect much gas. But expanding the mass range, give a sense for how much dispersion there of the gas star ratio as you raise the galaxy mass?
That's a good question. I don't know off the top of my head, but I can tell you that these star-by-star simulations are very hard when you increase the mass too much, because the reason why I'm able to reach redshift zero at all is actually because they are quenched by reionization. So that's kind of a nice feature of these galaxies. And that kind of means that there is no gas left at redshift zero, because if there were, there would be star formation. But no, it's a good thing that I can look into the other simulations that we have, where we don't do this star by star.
Simply you go to higher mass sources, they're pretty actively star forming. So.
Yeah, if you reach like 10 to the 10, 10 to the 11, then you even find starbursts, right?
Thanks for your talk. I was a bit confused about the last part of your talk where you tried to compare observations and said that the magnitudes are systematically underestimated or overestimated. So, I mean, that does not, doesn't that mean that the model that you're assuming is wrong? Like, because if your background was consistent, then you should have recovered what you put in, right? So there's something.
I think it's more subtle than that. The background could be one aspect. I think it's more a matter of like when we run simulations, we don't estimate half-life radius this way. Like we just take the half-life radius as like this is the actual half-life radius of the simulated thing, and if you don't keep in mind that your profile might not be a nice exponential, you will make a mistake here. And I think it's a matter of defining the parameters the same way.
So what you're trying to say is that the first term is what's being mismodeled, not the last, not the background.
Yeah, okay, so this half-life radius for the crosses, that's this term here. But for the stars, how you would typically do this from a simulation point of view is you would actually just derive the half mass radius even.
Okay. And are you saying that would not necessarily follow that profile? Like it won't have an exponential or something like that. Is that what you're trying to say?
Yeah, exactly. It's more of if we want to do better than this, I would say like getting a multi-component model, like getting something like this. Like for example, this is quite nice and exponential in the inner region, but then adding another component that takes into account the outer region. And there's actually been attempts to do this in the literature.
So for this one, you are saying that the simple exponential profile is not adequate enough to capture the complexity of the structure of the galaxy. And the slide earlier, you mentioned cutting off to get only the upper giants, and I was wondering whether that has an effect at all.
So I think it does have an effect. But the thing is that when I cut off the giants, then it's very hard to see this, right? You cannot distinguish this from the background.
Because of your numbers or because they're distributed differently than the underlying population?
So in the case of this example, when I only have over 50 stars, they completely disappear and they're just eaten up by this term. And you don't even see it in the errors from the statistics. In this case, if you were to observe it near enough where you have thousands of stars, you can actually start eventually seeing this. I haven't done it yet, but I should go in and do this for something like the LSST deepest observations and see when is this actually observable and what fraction of stars do we actually estimate to be in this system. And also, does this have these are typically from accreted material, so they might have different chemical signatures, etc. But yeah, this is all. There's a long list of to-dos.
Does anyone else have a question? Does anyone online have a question? Okay, if not, I have some questions. So the first one I wanted to ask was, so you showed like 2 different runs with and without star by star simulate like prescriptions, and the galaxies look different. Like one was much bigger. Is that just because you have like core collapse supernova starting off later?
You mean when I showed the structure?
Yeah,
Yes, like
yeah,
the particles?
are the differences because of like core collapse starting later?
So this is a bit of a cheat, actually. So these are the same simulation. Just I took the individual stars here. I know which particle form together, so I just grouped them again in post-process. And so these are like it's a matter of resolution. Like they have the same structure, like this screen here is here. The problem is that it's 4 particles, so it's very hard to see. So this is just an example to show like what does this imply in terms of resolution. I think the better comparison is to look at this, right? Where we actually, so these are now star by star, and these are not star by star. And I think part of the shift here has to do with feedback strength, and you have to make some different assumption for your feedback injection when you do star by star. For example, wind injection is quite different in these 2 models. Supernova is actually very, very comparable. There is a different assumption on the IMF actually. In these 2, there's a different lower limit. And I think that actually makes more of a difference than we would have hoped, let's say. So yeah, but I think, or at least what I want to investigate, running identical models with and without star by star, to see like are some of this shift due to the fact that we're now resolving the IMF and actually sampling the IMF, and then I guess introducing these kind of differences.
I have another question. Actually, 3 questions. So the first thing is, how do you decide what kicks the stars get? Is it drawn from some Gaussian with some spread?
It's based on results from one group 2016. So it's based on this distribution here. This is the velocity distribution from n-body simulations.
Okay.
It's actually it's actually a single cluster of 10 to the 4 solar masses, and then I apply this distribution to all the stars. Well, not all the stars. I assume this is the distribution of all ejected systems. So I make an assumption on how many stars are ejected from population. Typically, this would be about 20% early on. And then I apply this velocity distribution to 20% of the stars. And in the end, what I end up with is something like a few percent runaways, the rest being walkaways. But I am working with a student to actually simulate star-forming regions from my simulations in this Torch collaboration, where we can actually do the dynamics properly, and then we can measure what runaway fraction should I actually get, and what velocity distribution should I put in.
Might be a good idea to compare against OE's results for runaways in the Magellanic Clouds. The actual observational statistics.
Yeah, so this I would say gives a bit high fraction compared to observations. That's depends on who you ask, but it's around less than 1% up to a few percent. This is roughly what I get out when I use this distribution with 20% ejecta. but there's a lot of uncertainty here. And it's also most likely a function of cluster mass. Now I just apply the same to all star-forming regions in my simulation, but if I could have a way to, what is the environment where these stars form, and how can I then link these kind of models to that environment? That would be the best, I think, but that's very tricky to do.
All right, I'll ask the next question later. Let's thank the speaker again. There's still many slots open for meeting one-to-one with Eric, so please sign up if you're interested. There's also cookies in the lounge, so we can all come upstairs for discussion.